In 1947, the admirals of the United States Navy were losing sleep over a problem that had nothing to do with atomic weapons or long-range missiles. The problem was simpler and more immediate than either of those threats, and the Second World War had demonstrated it in terms that no professional naval officer could pretend to misunderstand. A warship operating beyond the reach of friendly aircraft was a target. It might be a capable target, well-armed and well-crewed, but it was a target nonetheless, a collection of steel and fuel and men that an adversary's aviation could locate, approach, and destroy with a systematic efficiency that the war had demonstrated repeatedly across multiple theaters and multiple oceans. The ships that operated within the protective umbrella of carrier-based aviation had survival prospects. The ships that ventured beyond that umbrella encountered torpedoes and bombs and, frequently, the bottom of whatever body of water they were crossing. Germany had learned this lesson from the British. Japan had learned it from the Americans. The Soviet military establishment, which had studied American operations with the careful attention of professionals who expected to be facing those same methods in a future conflict, had drawn exactly the same conclusion from the other direction. Find the ships outside the aviation umbrella, and they are yours. American naval planners understood that their adversaries understood this. And they understood something else. That the carrier aviation umbrella, however powerful and however central to American naval doctrine, had a geographic limit. Carriers could not be everywhere. The vast oceanic distances that American naval strategy required covering, the convoy routes and patrol zones and forward operating areas that the strategic situation demanded, could not all be within range of carrier-based aircraft at all times. There would always be ships beyond the umbrella, and those ships would need some form of aviation protection. The concept that emerged from this strategic reality was audacious in the way that only proposals made by people who have thought carefully about an impossible problem can be audacious. What if any ship, not a carrier, not a ship specifically designed to support aviation operations, but any destroyer, any cruiser, any escort vessel, any transport, could carry its own air defense? What if an aircraft could be designed that required no runway, no catapult, no arresting gear? An aircraft that took off vertically from whatever clear space was available on a deck, flew as a combat aircraft should fly, and then returned to land vertically on that same small deck space, regardless of what the sea was doing beneath it? The idea required roughly 5 or 6 meters of clear deck. Nothing more. Every ship in the fleet had that much space somewhere. The program that the Navy established to investigate this concept received a name that evoked precision and delicacy, a reference to the smallest and most agile of birds, capable of hovering in place, moving in any direction, stopping instantly. The name was gentle. The engineering requirement was not. The machine had to take off vertically without any forward motion. It had to transition from vertical hover to horizontal flight, accelerate to the speeds of a combat fighter, perform whatever tactical tasks its mission required, and then return, transition back from horizontal flight to vertical hover, and land on a ship's deck in sea conditions, with the deck moving in multiple axes simultaneously. No aircraft of this type had ever been built. No aircraft of this type had ever been flown. The question of whether an aircraft of this type could be built and flown was, in 1947, genuinely open. 2 aircraft manufacturers received contracts in 1951 to investigate the question. Each was to build 2 prototypes of their proposed design. Neither company ultimately built more than 1. The engineering challenge was severe enough that producing a single example consumed resources that would have been required for a second. And the lessons learned from the first were sometimes discouraging enough that pursuing the second seemed inadvisable. One company produced an aircraft that failed to complete the full vertical to vertical flight cycle that the requirement demanded. The other company produced something that its creators described with various degrees of technical precision, and that observers who saw it for the first time described with degrees of bewilderment that the technical precision did not capture. The aircraft built by this second company was called the Pogo, and the history of what it did and why it ultimately did not matter is one of the more instructive stories in the history of aviation development. The first thing that anyone who encountered the Pogo needed to understand was that it was designed to stand on its tail. Not to land on its tail, not to take off from a tail-sitting position as a transitional arrangement, but to live on its tails, to be parked on its tail, serviced on its tail, loaded on its tail, and launched from its tail. The aircraft rested on small wheels mounted at the wingtips and at the tips of the tail fins, pointing its nose directly at the sky. The cockpit was oriented so that the pilot sat essentially on his back, looking straight up through the canopy at the sky above. At the nose of the aircraft, which pointed skyward, two large counter-rotating propellers waited to pull the entire assembly into the air by brute force of rotational thrust. The delta wing planform, an unusual choice for a propeller-driven aircraft, more commonly associated with high-speed jets, provided a broad, stable lifting surface once the aircraft transitioned to horizontal flight. Two vertical tail fins, one above and one below the fuselage centerline, provided directional stability in both flight regimes. The total package was approximately 9.5 meters long with a wingspan of about 8 meters, powered by a turboprop engine delivering nearly 5,000 horsepower to the two counter-rotating propeller discs. The counter-rotation was essential. A single large propeller spinning in one direction would generate a torque reaction that would spin the aircraft in the opposite direction, making control essentially impossible in the vertical regime. Having two propellers spinning in opposite directions caused their respective torque reactions to cancel each other. The performance projections on paper were respectable. Maximum speed in horizontal flight was expected to reach somewhere between 650 and 800 kilometers per hour, depending on configuration and altitude. The aircraft would be able to engage the types of aircraft that a Soviet adversary might use to attack surface ships. The concept was coherent. The question was whether the concept could survive contact with the physical world. The answer to that question was developed in an aircraft hangar at a California Naval Air Station over the course of several months of tethered trials before anyone attempted free flight. The trial methodology reflected a clear-eyed assessment of the risks involved. Nobody had flown a tail-sitting aircraft of this type before. The control inputs that would be needed to maintain stable hover were not fully understood from theoretical analysis alone. The propeller downwash interacting with the ground surface at close range would create aerodynamic conditions that were difficult to predict analytically. A failure at low altitude during a first free flight attempt, a loss of control, a sudden uncommanded roll or pitch, would be fatal both to the pilot and to the prototype. The solution was to attach the aircraft to a system of restraining cables before asking anyone to fly it. One cable connected to the nose, running upward to an overhead attachment point, prevented the nose from dropping forward during vertical hover. Two additional cables attached to the wingtips prevented uncommanded rolling. The system was clumsy and would never be used in operational conditions, but it provided something more valuable than elegance. It provided the margin for error that any genuinely novel aircraft required during its first contact with the physical realities its designers had approximated in analysis. The pilot who occupied the cockpit for the tethered trials possessed a combination of professional qualifications and personal characteristics that the program needed, and that most people would not have recognized they needed until they thought carefully about what was being asked of whoever sat in that seat. He had extensive flight test experience. He had the analytical capability to identify and articulate what a machine was doing in real time, under conditions that precluded deliberate thought. And he had the specific temperament that the circumstances required, not recklessness, which would have killed him in the first weeks of the program, but a measured acceptance of risk that allowed him to continue working on a machine that was regularly demonstrating new and unexpected ways in which it might kill him. The first engine runs inside the hangar immediately revealed the scale of one problem that the designers had understood in principle but had not fully quantified. Two large counter-rotating propellers accelerating to operational speed generated a downward airflow of considerable velocity and volume. In the confined space of the hangar, this downwash struck the floor, reflected off the walls and equipment, and returned as chaotic upward gusts that buffeted the aircraft unpredictably. The restraining cables went taut repeatedly as the aircraft tried to roll or pitch in response to these reflected flows. Personnel working inside the hangar during these tests needed to hold on to fixed structures to remain standing. The pilot, sitting nearly on his back in the cockpit, operated the controls continuously to counteract the disturbances, and several times, only the cables prevented the aircraft from rolling onto its side, which would have driven a propeller tip into the concrete floor at high rotational velocity. This phase of testing continued for months. The pilot accumulated more than 60 hours of tethered time in the aircraft, an extraordinary number for a machine that had not yet left the ground in free flight, during which the engineers refined control system parameters, adjusted engine management procedures, and gradually converged on a configuration that was controllable enough to attempt freeing from the cables. The pilot developed an understanding of the aircraft's behavior that went beyond conscious analysis into the reflexive category, the kind of physical intuition that experienced pilots develop for familiar aircraft, and that this pilot was developing for a type of aircraft that nobody had ever flown before. On the first day of August in 1954, the aircraft was moved to an outdoor area and the tethers were reconfigured for free flight operations. The cables remained attached, but were now connected to ground anchors rather than to an overhead structure, providing restraint against catastrophic excursions while allowing genuine free flight within a limited envelope. The engine was started. The propellers accelerated to flight power. The aircraft rose from its tail-sitting position, climbed to approximately 6 meters, hovered briefly, and descended. It had been airborne, freely, controllably, intentionally airborne. Over the following days, the altitude of the hover tests increased. 6 meters became 15. 15 became 45. The aircraft behaved consistently with what the tethered testing had suggested. Controllable, but demanding, requiring continuous active inputs to maintain stable hover and sensitive to any distraction or hesitation in the control sequence. The pilot managed it. The aircraft responded. The concept was working. On the second day of November 1954, the transition from vertical to horizontal flight was attempted for the first time. The aircraft rose from the ground vertically, as it had done scores of times before. Then, at altitude, the pilot reduced the nose attitude, allowed the nose to drop from pointing skyward toward the horizon, then below the horizon. The tail rose. The aircraft rotated from vertical to horizontal. Forward, airspeed developed. The wings, which in vertical hover, had been providing no aerodynamic lift at all and were simply structure, began generating lift as the airspeed increased. The transition from thrust-supported vertical flight to aerodynamic lift-supported horizontal flight was accomplished. The pilot flew the aircraft in horizontal flight for 21 minutes. Then he reversed the process, reduced speed, raised the nose back toward vertical, transitioned back through the regime where thrust was replacing aerodynamic lift, and arrived in stable hover. He descended and landed. No American aircraft of comparable capability had done this before. The sequence, vertical takeoff, transition to horizontal flight, horizontal flight at combat-relevant speeds, transition back to vertical, landing had been completed. The concept that the Navy had been funding since 1951 was physically achievable. The performance in horizontal flight was striking to those who observed it. Even at reduced power settings, the aircraft accelerated to speeds that challenged the chase aircraft assigned to monitor and photograph its maneuvers. The chase aircraft lost visual contact with the prototype more than once as it accelerated beyond the pursuit aircraft's ability to keep pace without itself going to maximum power. For an aircraft sitting on its tail on the ground, the horizontal flight performance was genuinely impressive. But as the horizontal flight testing expanded and the flight envelope was explored more thoroughly, the problem that would ultimately determine the program's fate became increasingly visible. The problem was not in taking off, the problem was in coming back down. To understand the nature of the landing problem, it is necessary to think carefully about the physical situation in which the pilot found himself during the final phase of every flight. The aircraft, having completed its mission in horizontal flight, had to transition back to vertical hover and then descend to a landing. During the descent phase, the nose was pointed skyward. The aircraft was moving downward, toward the ground. The ground was below the pilot, behind him in terms of his visual orientation. He could not look straight down and see where he was going. His forward field of view was directed upward and somewhat forward toward the sky. To see the landing area, the pilot had to twist in his seat and look sideways and backward over his shoulder. He was trying to assess his height above the ground, his lateral position relative to the landing target, and his rate of descent, all simultaneously, using a visual reference that required awkward postural contortion and that provided incomplete information about the actual parameters of the approach. The engineering response to this situation was an altitude monitoring system connected to a 3-light indicator in the cockpit. One light indicated stable hover with an acceptable descent rate. A second indicated an elevated descent rate that remained within acceptable bounds. A third indicated that the descent rate had exceeded 3 meters per second and that either additional thrust or contact with the ground was imminent. The system was a radar altimeter connected to 3 colored lights. It told the pilot how fast he was falling, but not where he was falling. Not whether he was positioned over the intended landing point, not whether he was drifting laterally, not whether the aircraft was tilting from vertical. The pilot developed a personal landing technique that worked within these constraints. Before transitioning to vertical hover for landing, he would approach the landing area horizontally at low altitude, identify specific visual reference points, commit their relative positions to memory, and then execute the transition to vertical. Using those memorized references, viewed through the awkward over-the-shoulder sightline, combined with the altitude indicator, he would manage the descent. It was a technique that relied heavily on pre-approach preparation and on the specific capability of the individual performing it. It was not a technique that lent itself to documentation as a standard procedure. The safety provisions for the pilot during this phase were minimal in ways that the pilot had accepted because the alternatives were unacceptable. The ejection seat that was notionally installed in the aircraft was recognized by the technical ground crew to be functionally unavailable during vertical hover operations. At low altitude, in hover, an ejection would project the pilot upward through the rotating propeller arc. The seat was effectively disabled without any replacement emergency egress provision being designed. The pilot's personal response to this situation was to fly every flight in the aircraft with the canopy open. Not partially open, fully open, at all speeds, and in all phases of flight: vertical takeoff, transition, horizontal cruise, transition back to vertical, descent, and landing. The open canopy provided the one emergency option available to him. If the aircraft were to become uncontrollable at low altitude during hover, he could physically climb out of the cockpit and drop clear of the aircraft, rather than remaining trapped inside a falling machine with a disabled ejection system. This was not a designed safety feature. It was the pilot's individual improvised response to an unsolved engineering problem. The program had no official emergency procedure for low-altitude vertical hover emergencies because nobody had written one, because writing one would have required acknowledging the scope of the problem. The aerodynamic phenomenon that made the final meters of the descent particularly demanding was a consequence of the same propeller arrangement that made the vertical flight possible. As the aircraft descended in hover, the two propellers were generating a high-velocity downward airflow, the same flow that had caused difficulties in the hangar testing. Close to the ground, this downwash struck the surface and rebounded upward along the sides of the aircraft in turbulent, unpredictable gusts. The closer to the ground, the stronger and more chaotic this effect became. In the final 2 or 3 meters before touchdown, the aircraft was being buffeted by aerodynamic forces that varied rapidly and unpredictably, requiring continuous corrective inputs from the pilot who could not directly see the ground he was approaching. The pilot made every landing successfully. His individual record over the entire test program showed no accidents and no hard landings. This was an extraordinary achievement, and he acknowledged it in a way that suggested he understood exactly how individual and non-transferable it was. Every landing, he said, was a personal improvisation, not a procedure he was executing, a contest he was winning. The difference between these two things was the difference between an aircraft that could be operated by trained pilots and an aircraft that could be operated by one specific pilot who had spent months developing a personal repertoire of reflexes and judgments that could not be efficiently transferred to anyone else. The Navy's observers understood what this meant. In May 1955, a second pilot, experienced, professionally qualified, with relevant test background, took over the aircraft to determine whether it was flyable by someone other than the original test pilot. The second pilot had not gone through the extended tethered testing phase that the first had completed. The equipment used for that phase was at a different facility, and time constraints had prevented arranging access. The result of putting an unprepared professional pilot into an aircraft that required a unique and slowly acquired skill set was exactly what the logic of the situation predicted. The first flight by the second pilot ended with the aircraft oscillating and yawing far beyond normal limits, saved from catastrophic rollover only by the retention of the safety cable system. The pilot was not deficient. The program was. It had produced an aircraft that could be flown by one person who had invested extraordinary preparation, and it had no viable path to producing more pilots of equivalent capability in any reasonable time frame. The Navy began its accounting. How many tethered training installations would be needed to produce enough qualified pilots to equip even a small fraction of the fleet with these aircraft? Where would these installations be built, given that they required fixed overhead infrastructure that could not be reproduced on ships? How would pilots maintain currency on the type when operating from ships with no access to the training infrastructure between cruises? And in the end, what would all of this produce? An aircraft that could not reach supersonic speed at a time when Soviet combat aviation was firmly established in the supersonic regime, with a fuel capacity that severely limited endurance, and with a landing system that was acknowledged even by its most capable pilot to be a series of individual improvisations rather than a reliable, repeatable procedure. The tactical analysis compounded the problem. The aircraft's vulnerability in combat was not simply a matter of speed disadvantage. The performance envelope of the adversary aircraft it was supposed to intercept allowed them to approach at altitudes and speeds where the pogo would be climbing toward engagement range while they were already in weapons release position. The endurance limitation meant that any sustained engagement quickly exhausted the aircraft's ability to remain in the fight. The specific scenario in which the aircraft could provide useful protection, 3 aircraft defending against a coordinated attack wave, was so dependent on adversary behavior, conforming to particular patterns, that actual adversary planners, who would not cooperate with American planning assumptions, could defeat it without particular difficulty. Meanwhile, the alternative that the Pogo had been designed to supplement was improving faster than the Pogo's own development was proceeding. Carrier-based jet aviation was advancing rapidly. Catapult systems were becoming more reliable and capable. Arresting gear was more sophisticated. A carrier-launched jet aircraft of the mid-1950s could reach speeds and altitudes and combat ranges that a tail-sitting turboprop could not approach. The Navy was building more carriers. The logic of the original concept, that ships without aviation coverage needed their own aircraft, was being displaced by the logic of expanded carrier aviation coverage itself. The prototype's mechanical condition added a physical deadline to the program's strategic decline. The reduction gear system that transmitted power from the turboprop engine to the counter-rotating propellers was operating beyond its designed service interval. The internal wear rate exceeded initial projections. The aircraft had been built as a research prototype, not as a production vehicle, and it was being used as a research prototype, intensively, repeatedly, under conditions that accelerated the accumulation of mechanical fatigue. The original test pilot, who had become the irreplaceable human component of the program, left to take other assignments. Without him, the aircraft's flight rate dropped and the program's institutional momentum dissipated. By autumn of 1956, the program continued because stopping it required an affirmative decision that nobody had yet made, not because anyone with authority believed it was leading anywhere useful. The engineering team at the company that had built the aircraft composed reports and presented proposed modifications. They discussed a more powerful engine version that had originally been planned for production aircraft. They outlined improvements to the hover stabilization system. They described potential weapon configurations, cannon or rocket armament that would have given the aircraft genuine combat capability if it ever reached a production version. None of these discussions produced funding. The second prototype that would have been needed to test any of these ideas was never authorized. In November 1956, the aircraft flew for the last time. There was no ceremony. The flight was not marked as a final flight at the time it happened, though subsequent events established it as such. The aircraft performed its assigned test program, landed successfully, as it always had when flown by someone who knew it, and was shut down. The engine did not run again. The program was officially terminated. The 2 years and several months of active flight testing, the hundreds of hours of tethered preparation, the singular achievement of one pilot who had made the impossible flight cycle routine through personal mastery, all of it concluded without fanfare and without the recognition that the scale of the technical achievement might have warranted in different circumstances. The aircraft spent several years as an informal landmark near the entrance to a naval air station on the Atlantic coast. It was not protected or maintained with any particular care. The climate of the Virginia Tidewater region, humid, salt-laden, cyclically freeze-thaw, worked on the airframe with the patient indifference of weather acting on unprotected metal. The aircraft faded and oxidized. Officers who passed it every day developed the ability to not see it that humans develop for any sufficiently familiar background element. Transfer to permanent museum custody in the early 1970s preserved what remained. The aircraft that had been the only tail-sitting turboprop fighter ever to complete the full operational flight cycle, vertical takeoff, transition, horizontal flight, retransition, vertical landing, entered the collection of a National Aviation Museum, where it remains as a physical artifact of what the engineering looked like when people who understood the problem tried to solve it with the technology that existed. The specific achievement deserves to be separated from the program's outcome before any final assessment is made. The program failed. The aircraft was never deployed, never produced in numbers, never changed the doctrine it had been funded to support. These are accurate statements. But they describe outcomes that were determined by factors external to the engineering question, by the trajectory of adversary aviation capability, by improvements in carrier aviation, by the economics of pilot training, by the mechanical limitations of a single prototype, by the absence of the one human being who had made the system function. The engineering question, whether a tail-sitting turboprop aircraft could take off vertically, fly as a combat aircraft, and return to a vertical landing, was answered in the affirmative. One pilot, flying a machine that had no functional ejection system, that required him to keep his canopy open at all speeds so that he could physically climb out if the aircraft departed controlled flight. That provided him with 3 colored lights in place of landing instruments, landed that aircraft successfully on every attempt over the entire course of the flight test program. The distinction between proving that something can be done and proving that something should be done is one of the more important distinctions in engineering history. The people who built and flew the Pogo demonstrated that tail-sitting vertical flight was physically achievable. What they could not demonstrate was that the circumstances of the mid-1950s justified the cost and complexity of making it operationally viable. The technology existed for the former. The strategic and economic conditions did not support the latter. The aircraft that stands in a museum today, or sits, properly speaking, resting on its tail in the attitude it maintained when it was a flying machine, represents that specific moment in the history of aviation, when one answer to a tactical problem was investigated seriously, found to be technically workable, and then set aside because the problem had been solved more easily by a different answer. The brilliance was real. The limitation was also real. Both of them live in the same airframe.